Many times so far, I have mentioned the word adjacency, and I was talking about the adjacency forming, etc. So one of the important things about OSPF is adjacency forming on interface, or I should say on the link. So when that happens, there is going to be a certain interface state machine that is maintained locally by the router, and interface goes through different states before the adjacency is fully formed. The information is exchanged during this adjacency forming, and only after the adjacency has been fully formed, when we have received the database information from other router, we can actually calculate the best path in our network. The best paths in OSPF are calculated using Dijkstra algorithm or shortest path first algorithm. So now I'm going to go through the adjacency forming. So what we are going to have here are two routers, let's say R1 and R2, that are interconnected using some link. So it doesn't matter which network type it is, I'll mention when there are some differences. And we want to form an adjacency. Now, the routers start by sending hellos. So the hello packets are first exchanged. Now, hello packets contain information like router ID, the area ID, the area type, hello timers, and a couple more parameters, but these are really the important ones. Now, once the hellos are exchanged, and once the router know about each other, they're going to proceed to form the adjacency. How do routers know about each other? So when router R1 sends this, it says, okay, this is my router ID. So at this point here, R2 knows about R1. But how does R1 know that R2 knows about it? Well, there is going to be one more thing. Well, there, as I said, a couple more things, but one more important thing. List of known routers or known router IDs on the segment. So basically, what's going to happen here, R1 is going to say, hello, I'm R1, and R2 is going to say, hello, I'm R2. In the next hello from R1, it's going to say, hello, I'm R1, and I can see R2. When R2 receives this packet and it sees its own router ID in the list of known routers from R1, it knows that R1 heard from it. The same thing goes in the other direction. So at this point, they can decide to form the adjacency. Now, they have actually started forming adjacency already. So let me first start at the beginning. The interface comes up. Depending on the interface, so let's say the interface state machine. When the interface initially comes up, there could be an initial wait state. Now, initial wait state will exist on broadcast and non-broadcast networks only, and will last for dead interval time. So whatever you configure to be your dead interval, this is how long the wait state is going to last for. Now, what is happening in the wait state? The routers are not sending any hellos, they're just listening and observing what is happening on the segment. Now, there was a question before when someone asked me, if I clear all the routers on the segment, will that take care of the preemption for the DR election? And my answer was yes, but don't wait too long, because some of the routers might actually might re-elect themselves, but you will have more than just a few seconds to do it. And this is exactly what I meant. The defense mechanism that I mentioned is this wait state. When you clear the process on the router, when the interface initially comes up on a particular segment, it is first going to spend this dead interval time, just observing what is happening elsewhere to see if the DR is already elected. If there is no DR elected, then the router is going to start the election process by claiming it is the DR. Now, during this time, you will have time to clear the other routers, and if, as I said, if you don't wait too long, you're going to be just fine with the election process. So this is that defense mechanism, and this exists there in the state machine to prevent unnecessary DR elections from happening. Now, the next state that you might encounter is going to be init state. Now, in init state, basically, we have sent hellos. So we are sending our hello. The next state is going to be two-way state. In this state, we have seen our router ID in neighbor's hello message. Now, I'm going to write here in green that this is a possible stable state. What I mean by possible stable state is when you have a network that, say, looks like this. So let's say that this is R1, R2, R3, and let's say that this network, that this router here is the designated router, and that this is DR other, so it's not eligible to be the DR, and this is the DR other. Let's say that we might have a BDR. It's irrelevant for what I'm trying to show you. So this is where we will have full adjacencies. But because this is a shared segment, because this is a broadcast network type, basically R1 and R3 will know about each other, and they will be in a stable two-way state. This is why I say that this is okay. The relationship here will be fully loaded is if everything is okay, but the relationship between R1 and R3 will be, okay, we know about each other, but that's about it. Nothing more. We have not moved on beyond this stage because we are not actually forming an adjacency. We just know that we exist, that we are on the same segment. So this is why I say here in this line that this is a possible stable state. So you could have a two-way relationship between two neighbors and that everything is okay in your network. Now, it could be an indicator of a problem as well, but for now I'm just going to indicate what the states do, and then I'm going to go through several examples what could cause the routers to be, for example, stuck in that state in a case that you need to troubleshoot what is going on. Now, after the two-way state, there is an exchange start phase. Now, in exchange start, I'm just first going to write it down, then explain. A master-slave relationship is formed, and decision how to exchange data is made. Now, let me explain this a little bit. So let's say that we have two routers, R1 and R2. So I'm going to say master slave just so you later on know what I'm talking about. So let's say that here we have a router ID of 1111, and here we have a router ID of 2222. Now, the master-slave relationship will be determined based on these values. This will be the master, this will be the slave. Very simple one. Why? Because this one has the higher router ID. Now, the role of the master is to paste the exchange and make the decision when to move on to another phase. The role of the slave is to do as told. That's what slaves do. Now, decision how to exchange the information is going to be made basically on the MTU size. So both of these routers, I need to learn how to write. Both of these routers here are going to exchange the information about what they think their MTU is configured on the interface. And if they are in agreement, as they are here, the master says, okay, we can proceed. If they are in disagreement, they cannot proceed. Even though the master might say override the slave, but this doesn't happen. If they are in disagreement what the MTU size is, they will not proceed at this point. So these are two important things that happen. Now, if they are in agreement about the MTU, the master is going to make a decision to move on to an exchange phase. In exchange phase, database descriptors are exchanged. Now, what are the database descriptors? So let me write that down. Database descriptor is summarized description of the database contents. So to write that in, or to say that in plain English, let me ask you one thing, and try to answer it for yourself. How many times have you eaten at a restaurant? Once, twice, or many times? Now, how many times have you gone to the restaurant and done something that I am dying to do at one point in my life? Just walk in and say, bring out all the food, bring me everything you have. And they bring out all the food, and you go, yeah, I'm just going to have this one strawberry. Thank you very much. You can drop the rest. Now, I didn't ask for I didn't ask for one of every, or a sampler. No, I asked just bring out all the food. So they brought out all the food they had back in the kitchen, and I picked one strawberry. Now, we don't do that when we go to restaurants, even though I'm saying I'm dying to try this out. What we do when we go to the restaurant is we ask for a menu. We are asking for a summarized information about what they actually have in their database, in their kitchen. So we take a look at the menu and say, yeah, I'll have strawberry, or whatever you want to have, right? So we take a look at the menu. We are not actually getting all the information. We are not getting all the food and throwing it away. We are getting information about what is contained in the database. This is exactly what the database descriptor is. This is the information I have in my database, and then I'm receiving from the neighbor the information that they have in their own database. So based on that information, I can compare the contents of their database with the contents of my database, and I can say, hey, you know what? This is the information that I would like to have. Bring this out. And the same thing happens. So this is the database descriptor. This is what gets exchanged in the exchange phase. It's basically an exchange of menus. This is what I have, this is what my neighbor has, and then we make a determination what is the information that we actually need to get. Which brings us to the next phase then, and the next phase is going to be loading. So at this point, we have actually determined what is the information that we need to get, and then we are going to proceed into the loading phase. Now, in the loading phase, the actual database content is sent. Now, The database content is sent using 3 types of packets. So database loading. So let's say that we have R1 and we have R2. So basically, R1 is first going to send something that is called link state request. So it is going to request a particular LSA, particular content, particular data from the database. To that, R2 is going to respond with something we call link state update. And when we have received this information, we are going to acknowledge that we have received this information with the link state acknowledgement. So these are separate packet types. So if we take a look at what we talked about so far, there are 5 types of packets in OSPF. We have hello, we have database descriptors, DBD, we have a link state request, we have a link state update, and we have a link state acknowledgement. Now, this is trivia for written test. Now, it's also useful for debugging. Because when you're observing, for example, debug IPOSPF adjacencies, you're going to see the hellos being sent. We need to know what is happening with the DBDs. So it says that, okay, too many DBD retransmissions. Hey, what does that mean? In which state are we stuck? Where we are stuck in exchange or exchange start. This is where the DBDs are exchanged. Now, if you're sending link state request, link state request, link state request, and you're not getting the updates, that means that there is a problem with the loading phase. So this is why, I disagree with the statement that, oh, this is just a trivia. Why would anyone need to know this? Well, if you want to be good at troubleshooting, if you want to be able to debug information and see what is going on in your network, it's very, very important to understand what these different packet types do and what is the information that is carried there. So this is the interface state machine at this stage now. And last but not the least, there is a last phase, which basically is full, which means database is in sync. And at this point here, I should write that this is a possible stable state. So there are only 2 possible stable states. That's full and two-way. All others are transient states, and if you see the router in any of those states for extended period of time, there is something wrong. So now that we know what is happening in different stages here, let's see what are the possible reasons for routers to be actually stuck in those phases. So let's write here troubleshooting adjacencies. So if we have init phase, what can cause the routers to be stuck for an extensive period of time in init phase? Well, the most likely reason is unreasonably long dead interval. Now, and there is a warning. Remember, dead interval on non-broadcast network types is 2 minutes. So that's, oh, sorry, disregard. I was writing one thing and thinking about a completely different thing. So if you have a router that is stuck in a wait state for unreasonably long time, look at the dead interval. This would be the #1 reason for the router to be stuck in this state for extended periods of time. So let's take a look at what is the possible reason for routers to be stuck in init. So if we have init and we are there for a long time, it usually means one way communication. Now, think about it. If we have two routers, so R1 and R2, and we are sending the hellos this way, that means that this interface here is in init phase. Now, if you're not getting hellos from the other side, what are the possible reasons? Well, one-way communication, which means that we are sending packets but the other side is not sending. Now, I'm not judging what is the reason for one-way communication. It could be simple that OSPF is not enabled here, or it could be that there is a layer 2 problem, or it could be that there is, something that prevents the traffic from this router, the OSPF traffic from this router arriving here. It could be access list, it could be police, or it could be any number of reasons, but one-way communication. Also, keep one thing in mind. I'm talking about the state of the local interface, which on this router you can see with show IP OSPF interface. Now, there is another situation, and that is if you run the command show IP OSPF neighbor. Now, if you ran show IP OSPF neighbor, let's say we have R1 and R2 again, and what you are seeing here is R2, and you can see it in init phase. Now, this doesn't mean that communication from R2 to R1 is not working. That means quite the opposite. That means that you are actually receiving the traffic from R2, but that there is some problem with your traffic reaching R2. Why? Because how else would you know that R2 actually exists unless you receive the hello? So it's important to know that this will show you the local state machine, and that this will show you remote state. So if you're running show IP OSPF interfaces, you are seeing the interface state on your own local interfaces, but show IP OSPF neighbors show you the information from the other neighbor. So that would be the number one reason for routers being stuck in init. Another would be hello mismatch. Now, hello mismatch means that some of the parameters in the hello packets don't match. What needs to match is the hello timer, the dead interval, the area ID, the area type, and the subnet. But the on point-to-point interfaces, that's not as relevant. So look out for those things. So hello mismatch, that could be the reason, and also one-way communication is a possible reason for the routers being stuck in this state. Now, let's take a look at two-way. Now, as I say, and I'm going to repeat this here, possible stable state. Which means that the routers could be in a two-way relationship, and that is possibly okay. But keep in mind that this is a possible stable state, which means this could also be an indicator of a problem. Now, let's say that you have two routers. R1 and R2. And let's say that this is Ethernet 00. And what we have here is that this is two-way and that this is two-way. And they are staying there. Now, this is going to be an indicator of the fact that on both sides you have set priority to 0. Now, if this is the case, they're going to be in a two-way state, absolutely stable, and you're not going to have a fully operational network. Because at least one of them needs to be DR here, because you are using Ethernet, which is by default the broadcast network type. Otherwise, you will not have the adjacency. Or, of course, you can change the network type here to point and avoid the DR and BDR election and this situation that they are stuck in two-way. But just remember, this is a possible stable state. The routers are not going to get out of this situation. As far as they are concerned, everything is fine if they are both with priority 0. So this is, at the same time, good news and bad news. This is why I wrote it. This is a possible stable state. So I'm just going to say that no DR was elected here. So that would be the reason for them being stuck in two-way. Now, mind you, of course, there are other reasons that they could be stuck, but I'm now giving you the most obvious one, sort of a checklist of things to go through. So, oh, I have the routers that are stuck in two-way. Let me check for the DR. Now, of course, there could be access lists. There could be any number of reasons that the routers could be stuck in this state, but as I say, I'm just giving you the most obvious ones. So the next one that we have is the exchange start. And the number one reason is the MTU mismatch. So if two routers are claiming different MTU size, this is going to be the problem. They are going to be stuck in exchange start. Now, there is one more reason, and that is unicast reachability. Let me explain that a little bit. So when we have two routers that are forming an adjacency, again, our R1 and R2, and we are sending hellos, so these are hellos, and when we reach the exchange start, let's say that this was a master and this was a slave, master is going to start speaking unicast with the slave, and slave is going to be responding back using unicast. So this communication between them is actually going to be unicast. So you can have a situation in which multicast hellos are operating properly, but unicast cannot make it across. If you have this situation, your slave side will be stuck in exchange start, very likely, but the master is probably going to move into the exchange phase and initiate this unicast communication. So if you have a situation that one side is stuck in exchange start and the other one is stuck in exchange, look for unicast reachability. So this is what I wrote here, is that unicast reachability could be the problem here. If they are stuck in exchange phase, number one reason for that is unicast reachability, just as I explained. Same reasons. The next thing is loading, and this is going to be the fun one. This can also be MTU problem, but I'm going to write it slightly differently. So let me explain this. Let's say that we have two routers, R1 and R2, and they are connected directly but through a switch. Now the switch could be Ethernet or frame relay, whatever it is, so this is the switch here. And let's say that this is R1 and this is R2. Now the MTU as configured on this interface here, let's say it's 1500, and MTU here is 1500. But let's say that the system MTU on the switch was set to 1480 or any number. Now, if we try to send a 1500 byte packet from R1 to switch, the switch will actually drop this packet because it cannot switch it. But in the exchange start, these two guys in exchange start, they exchange this information, so the two of them actually agree about this. Now, let's say that you have a situation that you have this happens at around 64. So let's say that we have 100 routes in the database here, and that we have 5 routes in the database here. When we reach the point of loading the database, this guy here sends only 5 LSAs, right? 5 LSAs can make it across, but this guy here needs to send 100 LSAs. What OSPF is going to try to do is it's going to try to pack 100 LSAs into as few packets as possible. Which means that the first packet is very likely going to be 1500 bytes. Which means that when this 1500 byte packet arrives to switch, it's going to be dropped. Which means that the link state request that R2 sent is never going to be responded to by a link state update. So there will be another link state request, link state update that gets dropped, link state request, link state update dropped, and eventually this router 2 is going to time out. But you're going to have a weird situation in this particular scenario where this side here says that the neighbor is loading and this side here is fully okay. Why? Because there were only 5 routes going in this direction and there are 100 routes going in this direction. And this is what I meant by underlying MTU mismatch. So something in your layer 2 is dropping this traffic. So if you have routers that are actually stuck in loading, this would be probably the #1 reason for it. So the next one is, of course, full. And as we know, this is a possible stable state. I say possible because there are still things that can go wrong. And if this is the case, we are all good. But sometimes we have situation that we are full but no routes in the routing table. If that is the case, the situation is database mismatch, or I should say database discrepancy, or filtering. So there are still reasons why the neighbors could be full, but you get no routes in the routing table. If you have that situation, the routers are in stable state, the database are synchronized, but there is some discrepancy in the database. The routers don't agree about some information in the database, and we are not going to trust information coming from this neighbor. If this is all good, this is where SPF is running, and we are all happy. So let me add SPF run to that previous list of these as well. So at this point here, we have SPF run.